Okay, so after discussing stellar astrophysics and stuff related to that, now let us move forward to binary star system. Okay, now the first thing which I have shown here is, let us discuss about the equipotential surface of binary star system. As you can see, this is a binary star system. So just consider 2 point masses M1 and M2, where M1 is greater than M2. Fine. Now I have drawn a line, and here this S is the center of gravity. So if a small a is the distance between M1 and M2, then this center of gravity is defined by this, right? So this is small a1 and this is small a2. So that a1 m1 equal to a2 m2. Okay. Now this is this xyz. Now we will be working in a co-rotating xyz Cartesian coordinate system. So basically, around this center of gravity, the two stars will be moving around this axis. So it is like this. They are moving around. Okay. Now next, what we will consider? We will consider an arbitrary point, say Q, over here, x, y, z, which is distance r1 and r2 from the two masses. Okay. So now, as I was saying, we are considering an arbitrary point Q, x, y, z, and which is at r1 distance from point m1 and r2 distance from point m2, and from the center of gravity the distance is smallest. Now you must remember that this is the axis of rotation, as I was saying. So the entire system is rotating around this axis of rotation, entire binary star system. Okay. So you can see the rotation is like this, and similarly here the rotation is like this. Okay. So the binary star system is moving like this. Okay. Now, so these are the relations for R1, R2 and S. You can check over here, and let us, as written here, the effective potential at this point Q. So this is the overall effective potential, the individual gravitational potential energies due to the two masses, and this is the potential for the centrifugal acceleration, half omega square s square. Now remember here, this omega square is given by the Kepler's third law. So this is more or less the simplified structure. So with this, now let us try to write the effective potential using all these relations and see what you get. Look at that. Okay, so these are the relations, right? 1, 2, 3. Now using this, we can write the gravitational potential at that arbitrary point Q, x, y, z. And this is the relation. You can check for yourself. Okay? That this is so. So basically this some constant into this entire term. এটা চেক করেছো? Fine. Now look into the structure. This part is R dependent. These are two constants. Here also these are two constants. This is again the separation. You can think of it that this is more or less fixed. This is also a constant. What about small s? Again it varies. Okay. Now here we will be talking about equipotential surface. That means where this potential is constant. Remember electrostatics? We talked about equipotential surfaces around charges and all that. Now here we will talk about gravitational equipotential surfaces. Okay. Now, in this matter, it is important to remember that this, although this is the entire expression, but these are the origins, right? So there are basically three forces together, one corresponding to each of the masses, and then the effect of centrifugal or rotational motion. Okay. So the question which comes to mind before we start drawing the equipotential surface is it possible that all these forces cancel each other? Why? Is it possible that all these forces cancel each other?
No, sir.
Now you have to check whether it is possible or not. Why don't you do this d omega dr equal to 0? Put this condition. Try to find. Do this. Okay. So, yes. No, let me just discuss this once again. So this is the overall potential arbitrary xyz. As you can see, it consists of three terms, 1, 2, 3. Okay. Now, someone just said me, sir, all the signs are negative, so we will not have anywhere where all the three terms cancel out. Fine. But just look into the structure. Okay, there is a saying which says the devil lies in the details. Okay, look into the structure. This is 1 by R1. Okay, so this is R1 in the denominator. Here R2 is in the denominator. What about omega s? This depends on s square. So basically, this means R1 and R2 in numerator. Okay? Denominator, denominator, numerator. Now, let me give you an example. Suppose I am talking about this function a plus 1 by a. Plot it as a function of a. So here you see numerator plus another term in the denominator. Now if it is just a, it will be like this, and if it is 1 by a, it will be like this, and if you do the sum, then overall you see there is a sort of, you see, extremum available, and this is because of the nature, different nature of these two terms. So same thing will happen over here, because of the fact that here it is in denominator and here it is in numerator. There will be scenarios where this term will be effectively, that means d omega dr will be equal to 0. Okay, now you have to do this yourself. D omega dr equal to 0. What are the places where this happens? Okay, now to find this, you can more or less qualitatively find this, but for that, first we have to draw the equipotential surface. Now I am not going to use any computer stuff, whatever. Let us just use very basic physics ideas. So this is mass m1, this is mass m2, this is the center of gravity S, this is our expression. Okay, now let me erase everything else over here. Okay, so let us consider a point here. What's so special about this point? You see, this point is very close to M1 but very far from M2. So effectively, I am choosing, effectively I am choosing R1 much less than R2. What will happen if I do such a choice? Look into the expression. Here, then this term will be effectively 0. Only this term will be dominant. Again, R1 less than R2. Okay. And here again, R2 square will be there, dominant. So it will be the competition between this R1 versus R2. But remember, in such a case, since this is very far, so let us consider an example, say 10,000 and 10,006. There is hardly any difference between these two. Okay? But what about 0 and 6? They are quite different. So this is what R1 is, this is how R2 will vary. You can think of it like that. Here, if we talk about an equipotential surface and just vary the values. So here, more or less, what I want to tell you that this value is very large. So overall, if R1 is small, it will be, the structure will be more or less like this. If it is very close to M1, further inside the center of gravity part. Okay, the same thing will happen for the case of M2, equipotential surface. And after that, what will happen is something like this. Since this is bigger, so it will be more, something like this. The structure will be like this. Okay, so the figure over here, I have enlarged it like this. Okay, so this is the enlarged figure. As you can see, this is the mass M1, this is mass M2. This is the equipotential surface very close to M1, same surface very close to M2. Now this is a different figure. See, this equipotential surface, this is somewhat deformed. Why it is deformed over here? Now this is the result of the effect from the other mass. Okay. Next, look over here. This is also somewhat deformed. And then if we move further away from the two masses, then we will get this point where the two touch each other. Okay, and this is the point where this d omega dr equal to 0. In fact, there are three such places, and these are known as 3 points. These points have particular name. They are known as Lagrangian points. Okay. So this is the inner Lagrangian point, L1, which is in between the two masses, and this one is extremely relevant for mass transfer. Okay, I will just explain briefly in a while. And these two are also important. Sometimes, why are they important? Now just consider about our Earth. We have our Earth over here. Then suppose this is the Sun, right? Now the nearest very heavy mass bodies near our Earth is Sun. So if we consider a system, this is suppose the binary system, forget about Moon, forget about other planets, then we will have similarly Lagrangian points. Now what will happen at those Lagrangian points? There the entire effect due to these two bodies will be overall 0. Taken into fact that the Earth is moving around the Sun. So this means that we can put satellites, not just satellite, space observatory. Okay. big telescopes we can put over there, and there will be no effect of the gravity of these two bodies. And why will you must ask me why, what is the importance of putting big telescope over here? Because as there will be no effect due to these two bodies, so they will remain in their position, and when they will take the measurement, there will be no effect of motion of the telescope. The image will not be blurred. Understand? But this is not entirely correct. Why? Because of the presence of other planets, even our moon. So even if this is a Lagrangian point with respect to Sun and Earth, because of the presence of other planets, satellites and all that, it will be somewhat approximate. So even if we put space observatory, in fact the International Space Station is also put at one of these Lagrangian points, it will have to be shifted from time to time. But again, if we put in some other place, then it will have to be shifted even more. Understand? So this means a loss of fuel. So we have to preserve fuel. So much better option, less manual operation, less fuel consumption. So put the big observatories, telescopes, all that at the Lagrangian points. Okay. Good. Now this view is basically the meridional view in the XZ plane over here, and this is the axis. Now as I was saying, suppose we have got a binary star system where two stars are there. Now as we have discussed in stellar astrophysics, what will happen after star burst? There are processes, hydrogen burning, helium burning, and so on and so forth. Even during the late phases of hydrogen burning, there is a very important stage. What is that? Red giant phase. What happens in red giant phase? The envelope expands. Now consider the case over here, or say over here. Suppose these are two masses. Okay. Now this star undergoes red giant phase. What will happen? What will happen is that slowly all this area is being filled up by the envelope of this M2. Again, slowly more and more expansion. So more filling up. More filling up. And then there will be a point when this filling up, this envelope, okay, this envelope, see what has happened? This exceeds this Roche Lobe area. The part of, you see, this was the original Roche Lobe. That means, what is the Roche Lobe? Roche Lobe is the surface, equipotential surface, which passes through the inner Lagrangian point. Now, this part of the envelope of this M2 star, the entire mass which has exceeded this Roche Lobe, what will happen to this? The result will be that this mass which has exceeded the Roche Lobe, it will lose the gravitational field of this mass. And as a result, what will happen? All this extra mass will slowly come towards this binary star system. But keep this in mind that this entire system is rotating. Had it been fixed, then it will just come over here, shoot. But it will not happen because this entire system is rotating. So what will happen is that I am just talking about this, say for example, the whole thing will come over here and it will rotate slowly around the mass. The entire stuff, okay, it will slowly rotate. Rotate and rotate and rotate, and as a result, an accretion disk will be formed around the star. And this is how accretion disks are formed. So basic explanation through mass transfer is how we do formation of accretion disk through mass transfer in a binary star system. This is very interesting. Okay, any questions? Now what will happen after that? This star will start gaining mass and this star will slowly lose its mass. And as a result, the stellar evolution, previously when the two stars were isolated, you can think of it, they were doing their individual evolution. But after this mass transfer, the evolution will become coupled. We will have coupled evolution. So this evolution has affected this evolution. Later on, it can happen in its stage of evolution that this star undergoes red giant phase. Then it will be feeding its extra mass which leaves the Roche Lobe to this star. Okay. So such scenarios are very common in binary star systems. Okay? Of course, I am talking about red giant phase. So just hydrogen burning, even not helium burning. Okay?
স্যার এখানে যখন মাস এর লোচে লোবের থেকে বেরিয়ে গেছে তখন তো মানে এর রোজে লোবের মধ্যে যখন নেই তো এর রোজে লোবের মধ্যেও তো নেই, তো এটা কেন টেনে নিচ্ছে?
No, the fact that it has exceeded the Roche Lobe of this fact means that it is outside the effect of the gravitational field of this mass. What else is there? The other mass. So, and remember, the whole stuff is rotating, it is not static. So as a result, it will be slowly, it will not happen immediately, but slowly it will be getting rid of the gravitational field of this mass. And what other gravitational field is present? What other forces? Two forces. One is the centrifugal and another is this mass. Okay.